Hello, and welcome to the 19th Annual Caithness International Science Festival and this evening's presentations entitled Meteorites in the Solar System. I'm Ian Bakey, Chairman of Science 03. With me here tonight is Nicola MacLeod, the Festival Coordinator, our presenter, Dr. Mike Sims, and also joining us from Caithness Astronomy Group is Gordon Mackey. Before we begin, a little bit of housekeeping. This event is being recorded, however your screens are not. This has been a very popular event, so please direct all questions through the question and answer button at the bottom and we'll answer as many as we can. As an audience, you have the opportunity to upvote questions, so if there's a question someone else has asked you're keen to have answered, give it a thumbs up to move it up the list. I'm now going to hand over to Gordon Mackey to introduce this evening's speaker. Thank you.
Thanks, Ian. Our speaker tonight is Dr. Mike Sims, a geologist and curator in the Department of Natural Sciences at the National Museums in Northern Ireland. I was lucky enough to visit the museum whilst in Belfast in 2019 and would highly recommend it to any who take a trip to the area. It's full of fascinating exhibits that Mike is heavily involved in producing. Mike has more than 150 scientific publications to his name, mostly covering the topics of geology, fossils, meteorites, and lichens. We're delighted that he is supporting the Science Festival this month by giving 3 separate presentations linked to these fascinating subjects. Tonight's topic is meteorites, something that has been in the UK news headlines over the past few days. I'll now hand over to Mike to give the first of his presentations titled Meteorites and the Solar System.
Right, thank you very much. Right, I'll share the screen, I guess. Right. Hopefully you can all see that. Well, I'm very pleased to be here this evening talking about meteorites on what is really a very, very auspicious day. It's 30 years since we had a meteorite fall in the UK, and there was the announcement today of another one, and not just any old meteorite, but an extremely rare type, which I'll say a little bit about, of course. So meteorites in the solar system. Some of the things I will talk about might look a bit complicated, but don't worry, because it's a case of just look at the sort of overall patterns. Don't worry about all the detail at all. So, right, meteors and meteorites. People often get these two confused. The media do all the time. A meteor is quite different from a meteorite, but a meteor may turn into a meteorite. A meteor is the flash of light which is caused by an object actually falling to Earth from space. It's traveling so fast it heats the air up around it, and that's what glows. And only if it hits the ground do we actually call it a meteorite. And the way to remember what a meteor is think of the early jet fighter, the Gloucester meteor, which streaked across the sky. Only if it crashed might you call it the Gloucester meteorite. So meteors are the flash of light, a shooting star, as it were. Meteorites are the things that go thud. They're bits of rock or metal that fall to Earth, and they're broken off much larger natural objects in space, and they've found their way to Earth, sometimes by long and circuitous routes. So those are actually meteorites. They are pieces from other parts of the solar system that we can't otherwise easily get access to. And what are meteorites made of? Well, there's of course there's simple classifications and less simple ones. I'm going to start with the simple ones. You've got iron meteorites, and a lot of people think, oh, meteorites are made of iron. Indeed, some are, but only about 5% of the meteorites that fall to Earth are iron meteorites. But the really big ones are the ones, this is 37 tons in Argentina. Then there's stony iron meteorites, which are really pretty rare. You're talking about less than 2% of meteorites. Like this is a slice of beautiful olivine crystals set into metal. So they're a bit special. They're a bit, quite beautiful compared with some of the other rather dull looking meteorites. So iron and stony iron meteorites. But about 85% of all meteorites are actually stony meteorites, which means, of course, they're made of stone. And there are 2 main sorts, and this is where we get into slightly technical words, but don't worry, there's one sort which are called chondrites. and chondrites are made of tiny rock beads. You can see this has been sliced through, and you can see all these things, little beads, which would be little spherical beads, have been sliced through, and those are called chondrules, which is why these meteorites are called chondrites. And the other type of meteorite, which is stony meteorite, which is actually much rarer, only a few percent are known, are what's called achondrites. And they're called achondrites because they don't contain any chondrules. They're made of crystals. You can see these crisscrossing crystals here, and they're just like volcanic rocks. They've cooled from a molten lava into these kind of crystalline state. But of course, it's not that simple. It's never that simple, is it? We've got more than 40,000 meteorites known, and in fact, you can divide them up into lots and lots and lots of different sorts. And most of these have come from their own separate little planet, which of course might have been smashed to bits. There may be very little left of it other than the bits we find. So you've got iron meteorites, and you've got these particular groups, which are based on their chemistry. And then you've got ungrouped ones, more than 60. So that's more than sort of 60 or 70 different planets that the iron ones came from. And then you've got these achondrites, various sorts, stony irons, not so many of those, and then the chondrite meteorites made of these little beads, and they fall into two main groups. There's a group here which all begin with C, and they're the carbonaceous ones, and then these are what's called the non-carbonaceous, and you'll see a bit more about the data. But the thing to remember here is it's very, very complicated, but it is possible to simplify it. So where do meteorites come from? Do they come from a galaxy far away? Well, no, they don't. They all come from within our own solar system. And the vast majority of them actually come from the asteroid belt, which is a zone of rocky material you can see sort of going around here between the orbits of Mars here and Jupiter there. And the biggest of the asteroids, called Ceres, is about 1,000 kilometers across. But there are tens of thousands of asteroids within this asteroid belt. But space is a really, really big place. So the chances of any of our spacecraft going to the outer planets crashing into an asteroid is infinitesimally small. And this is just a shot of asteroid Itokawa, showing the size compared with the International Space Station. I'm not suggesting the International Space Station is orbiting this asteroid. This is a sort of a medium-sized one, you know, 0.5 kilometer across. But there are few meteorites come from the moon or from Mars, and that's where you get a really big rock, a really big meteorite hits the moon and it flings bits of rock into space, and some of those have actually found their way to Earth, and we pick them up as meteorites. And how do we know they come from these places? Well, you could say, well, the ones from the moon obviously are made of cheese, and the ones from Mars obviously made of chocolate. But no, it's a case of we compare them with rocks that we know of, that the Apollo moon rocks, which were brought back, and the moon rocks, the lunar meteorites were a very good match. And then we compare these ones that we suspect come from Mars with the results from the various Martian landers, the sort of Spirit and Curiosity, and even the Viking landers going back to the 70s. So we know that we've got a few meteorites from the moon or Mars. And how do they get here? Well, all meteorites, the beginning of their journey involves a collision of some sort, where you get two asteroids. Yeah, there's no traffic control up there in the asteroid belt. Most of them are going around sort of sedately in their own orbits, but every now and then you will get a collision, and that sends pieces off in all directions. And you might think, well, that's how they get here. They just keep going. But in fact, that's not the way that it happens. That's very, very inefficient to just have a collision sending the bits off. There's another mechanism that actually ensures that meteorites get here more efficiently and more quickly. So they all start off with collision between an asteroid generating lots of small pieces. And then they are hurried on their way when they venture into what's called a Kirkwood gap. And these are named after the chap who discovered them, this guy here, Daniel Kirkwood. And he noticed that the asteroid belt wasn't sort of equally populated by asteroids all the way through. There were these zones that had, you know, some asteroids, and then in between were these bands where there was almost nothing or very, very few asteroids. Something was preventing any asteroids staying in these bands. And the key to how meteorites actually get to Earth is all to do with what happens if anything inadvertently wanders into one of those Kirkwood gaps. After a collision, bits will get zinged off and some of them will find their way into one of those Kirkwood gaps. And what happens next is how they actually get here. And it works a bit like a swing. This is my son many years ago, in that what happens with these bits that have wandered into a Kirkwood gap is they are given a nudge every now and then, or quite frequently, they're given a little nudge which speeds them up or slows them down. So in a swing, you only have to give it a little bit of a push and it goes higher and higher and higher. You don't need to put much energy in it to get it to move. What you're doing is you're working with its resonant frequency. So things that move into the Kirkwood gaps are given regular pushes from something. And you think, well, what? And it's all to do with Jupiter. Jupiter is the biggest planet, of course, huge gravitational pull. So it has an effect on anything that it is vaguely close to. And what I'm going to do is look at what happens to anything that happens to stray inadvertently into what's called the 3-to-1 Kirkwood gap. And here's the main Kirkwood gaps. You've got 3-to-1, 5-to-2, 7-to-3, and 2-to-1 favorite. It sounds like horse racing odds, but what they are is the number of times our little stray meteorite or stray asteroid goes around the sun compared with how many times Jupiter goes around the sun. So 3-to-1, we have 3 orbits of the asteroid, 1 orbit of Jupiter. And I'll show you what happens as it goes on. So here we are at the beginning, they're kind of lined up. So Jupiter's going to be giving this thing a bit of a tug. And off they go. And you see the asteroid's halfway round, and it's lap 1, it's done a lap. But when Jupiter's got halfway round, our little asteroid is already 1.5 laps, and it lines up again. And you keep going, bang. So for every every 1 orbit of Jupiter, our little asteroid actually meets up twice and is given a sort of bit of a tug. So that might be every kind of 6 or 7 years or so. And basically it's kind of pulling its orbit, it's speeding up or slowing it down, and that has an effect on where it goes. So here we go again. You can see up here at the top, the star is our little kind of asteroid that's had bits knocked off it, and they have wandered into one of these Kirkwood gaps, and off it goes. It starts off, they all start off in a fairly sort of close to sort of circular or slightly elliptical orbit, but it's being tugged at regular intervals. And as that happens, because it gets sort of speeded up or slowed down, its orbit becomes more and more eccentric, you see. And this is Earth is the blue one just here. So watch out, Earth. Oh, it just missed, you see. And so it goes more and more eccentric sort of orbits. And if Earth happens to be in the way, at some point, bang, it actually lands on Earth. But of course, Earth is quite small in the great sort of vastness of space. So unfortunately, most of them are going to actually miss. And a lot of them will end up either flung out of the solar system or flung into the sun, which is, to my mind, a terrible waste. And of course, they can land on other planets. They could land on Mars. And quite a few meteorites have actually been found on Mars now. So that is how they get here. They stray into the Kirkwood gaps, and their orbits become more and more eccentric. They get sent out of the asteroid belt, and they go into what's called Earth-crossing orbits. And if we're lucky, the orbit of the meteorite actually coincides with the orbit of Earth, and we are all immensely happy. And they arrive on Earth, and this is astonishing. This is just like a week ago, 28th of February. This is this amazing sort of fireball, really, really bright fireball, which was caught on lots of doorbell cameras. Who would have thought that doorbells could ever contribute anything to space science? But they do now. It's an amazing thing. This is here on the right, we have a map of all the observers. More than 750 people observed this meteorite. And you can see all these people, they're looking north. And you can see these, you can see their faces, so they're looking south. You've got some here looking east and a few sort of looking west. So you can tie it down. You can tie it down fairly well where this thing is going to come down. And though all those doorbell cameras, we know exactly where the doorbell cameras are, and you can go and we can get the data as to what direction they're looking. And there are also specific cameras that have been set up by meteor enthusiasts to actually record these events, and they record the data on the trajectory and such like. And by piecing these together from perhaps half a dozen or more these things, we can get an amazingly accurate trajectory for this actual object, and we can work out how fast it's going, how steeply it was coming in. We can work out, we can effectively kind of wind back into the solar system and work out where it was coming from, which is not exactly, but roughly where in the asteroid belt it was coming from. And this, with all this data, it's possible to produce what's called, this is the trajectory coming in. It was coming in fairly steeply, but it was actually going quite slowly. It was only doing about 11 or 12 kilometers a second, which sounds quite fast, and it is, but for a meteorite, it's quite slow. So it wasn't torn apart quite so severely as it might have been by the stresses coming down through the atmosphere. And this is the sort of flight when it's actually luminous, but as it slows down, eventually the air around it is not heated up so much, so it goes into dark flight mode, and we can predict or project that it's going to fall somewhere here. And the orange is where the best places are, and the blue and purple are places that are not so good. And I came across the fireball footage within an hour or so of it happening. I didn't see it though. And then the following day, I was alerted to this strewn field was sort of issued as it were. And I looked at it, I thought, oh my goodness. I don't know, you can possibly just about make out here, there's a little place there called Bishop's Cleeve. It's a little village, well, it's a big village actually, a bit north of Cheltenham. I grew up in Bishop's Cleeve. My mother still lives there. Unfortunately, she's 95, so she's not really up to going out looking for the thing, but it was astonishing that here we have a meteorite that actually bits of it landed in my home village. You couldn't make it up. And this is one of them. Teams from Glasgow University, Plymouth, Natural History Museum, Imperial College, and other places went along using the data from all the observations and the strewn field, projected strewn field, and they found a few pieces. And this is probably the nicest of them here. My wife actually says it looks a bit like a dog poo, but it's much, much more important than that. So we have found pieces, which is fantastic news, really, really amazing, but so frustrating that it fell on my own home village and I can't be there. So, okay, now another thing, moving on, we've figured out, how they get here. From the data that we get from observations, we can wind back to find out where it came from. And one of the things that you think, well, how can we possibly know that? How long does the journey take? From it starting out as a chunk knocked off a big asteroid, so a chunk perhaps less than a meter across, how long does it take to get from there to Earth? And we can actually do that. It's amazing. Because these things, when they're in space, they're subjected to cosmic ray bombardment. And cosmic rays are incredibly energetic particles that come from supernovae. Very damaging. It's one of the big risks for anybody going to Mars. They're going to be exposed to cosmic rays for kind of 6 months, which, they can do a lot of damage, because if they hit an atom of, well, for instance, we got down here, sodium-23 atoms, so only sodium-23 atoms in this meteorite. If they get hit by one of these cosmic rays, it may well change it to neon-21. And these new elements are what's called cosmogenic elements. And essentially, the longer the thing is in space, the more of this neon-21 sort of isotope accumulates. It's a bit like you stay out in the sun too long, you get redder and redder and redder. And that's essentially the same sort of thing, but a bit more subtle in these meteorites. So when they land, by careful analysis, you can measure how much of this neon-21 is actually in your meteorite. And you can work out from that, assuming that the cosmic ray background is fairly constant, you can work out how long it is actually taken to get to Earth from being knocked off a big asteroid, which is actually an amazing thing to be able to do. And here's some actual results. How long have these things been in space? And I'm looking at a few types of meteorites. This is what's called CM chondrites. This new meteorite that's fallen in Gloucestershire is actually CM chondrite. It's a very light and crumbly meteorite, not as appallingly crumbly as these things. There's only 6 of these known because they're so crumbly that first drop of rain, they just turn to mush. So you never find them after the event. You have to more or less have picked them up the moment they land. But these very crumbly meteorites, you can see the age you get that they've been in space is relatively small, but it's really quite short. Most of them, you're talking a few 100,000 years to perhaps 5, 6, 7 million years. So they've not been out there very long. And that's because if they should happen to sort of ding into anything else, they'll just get pulverized. And so they'll just end up as just dust. But then we look at really tough meteorites, and iron meteorites are tough, which is why all the really big meteorites on Earth are iron meteorites. And look at the ages of these, 500,000 years, getting on towards 750,000 years, because they can go around the asteroid belt, dinging into other asteroids, and they're not that bothered. Bits will get knocked off, but they will survive. So tough meteorites have a much longer time, whereas these things kind of disappear pretty quickly. And this brings us to a third group that I'm just going to mention as an interesting little aside: pallasites, which are those beautiful stony iron meteorites which have olivine crystals set into iron. Absolutely beautiful things. And they're pretty tough. So you're talking about like 100, 200 million years perhaps. There aren't a huge number of these dated, but so they're fairly tough, which we'd expect. Not as tough as the iron meteorites, but much tougher than these. And but then it brings us to this thing. This is a thing called the Shirakovsky meteorite, which was a meteorite fell in the frozen reservoir, the place called Shirakovsky in Russia back in 1956, and it disappeared through the ice into the murky depths. And divers went down and they didn't find anything. And then in 2003, it was said that a diving expedition had gone there and they had recovered about 150 kilograms of this sort of dense meteorite, which when they sliced it, turned out to be one of these beautiful pallasite meteorites. And of course, meteorite collectors got very excited and paid really quite high prices for such slices of this thing. But eventually a piece found its way to one of the laboratories which does analyses on meteorites. And they looked at various sort of aspects of it. They thought, this is very strange. There's lots of things chemically about this that are very odd and unlike any sort of meteorite. And then when they looked at the cosmic ray exposure age, which should show at least some evidence of that, they said, no, this thing hasn't been in space at all. This is a fake meteorite. It's the only kind of truly fake meteorite. Somebody specifically made this to deceive meteorite collectors and make lots of money. And they did make a lot of money, tens of thousands of dollars from bits that they sold. So this is where there's a sort of other unexpected use. It proves that this was in fact a fake meteorite. So that's a really interesting cosmic ray exposure age, looking at how long they've been in space. And now I'm going to look at one particular meteorite, the L chondrite. Don't worry about what an L chondrite is, but they're the most common type of meteorite. There's about 38% of meteorites that fall are in fact these type meteorites. And in fact, the Strathmore meteorite that fell in December 1917 is an L chondrite. That's near sort of Perth. And when you look at this graph here, you see most of them are way up here. They're 10, 20, 30, 40 million years or more. They've been in the wilderness before they arrive on Earth. They take a long time to get there. They're fairly tough meteorites. But a few of them, just a few, get here really quickly. You've got 4 take less than 1 million years, and some of them are just taking 200,000-300,000 years. They've got here really, really fast. They've clearly got on a very, very good bus service, but it doesn't run very frequently. Whereas these have got on a really kind of slow bus that runs every half an hour. So why have some of them got here so fast, but most have not? And that's what we need to do, is go back to look at Mr. Kirkwood again and his Kirkwood gaps. And the thing is that not all of these Kirkwood gaps are equal. Some are much better than others at sending meteorites to Earth. And there's 2 here. Don't worry about this, the mu6 resonance and the 3-to-1 gap, which was the one that we looked at, for every time Jupiter goes around once, it meets up with our little asteroid twice. So 3-to-1 resonance is really good. So a lot of things that fall into that one are going to head in towards Earth. But these others, the 5-to-2, 7-to-3, and 2-to-1, are really pretty lousy. Less than 1% of the bits that end up in those Kirkwood gaps are going to head out to Earth. A lot of them are going to head out of the solar system. And what use is that to anybody? And it turns out that we know from looking at these trajectories, as I was saying, if we got all these doorbell cams or whatever, we can actually work out where these things are actually coming from. And we know that the the parent body, the parent little planet that the L conduit's coming from, is close to the 5-2 gap. And that's lousy for sending things to Earth. But less than 1% will head to Earth. So those ones that got here really quickly are the few that went in there and headed out to Earth. Most of them got headed out to the solar system. All the ones that took tens of millions of years to get here have had to crawl their way across as a part of the sort of the asteroid belt to that next Kirkwood gap, the 3-1. So it's a very fast bus that doesn't run very often, as opposed to a very slow bus. It's a long walk to get to the slow bus that runs every half hour. So that's why most of them take a long time to get here, because they've had a long, long crawl to get to the right bus stop. Right, how did the solar system form? Well, that's a big question, isn't it? If we go back right to the very beginning of the solar system, he started out with a cloud of dust and gas. We see these out in this is, I think, part of the Orion Nebula, and we see them out in space, and we know that this is the sort of places where planetary systems actually form. But how do you go from that to lumps of iron or stone? You know, how do we do that? And what happened, we think, in the case of the solar system, you had this big cloud of gas and dust, which is probably several light years across, collapsed in on itself, and that was triggered by a supernova, which is an exploding star, incredibly energetic event, and that caused the thing to sort of collapse. And one of the byproducts of that is it spat lots and lots of an isotope called aluminium-26 into the dust. And so aluminium-26 is radioactive. It has a half-life of 720,000 years. So it means that after about 4 million years, there's none left. It's all gone. But it means that those planets that form very early on in the first million years or two, they're going to have radioactive dust in them, and that's going to heat them up. And that's really, really important to understand how the planets formed and how our Earth formed. So the first thing that happens after this dust cloud collapses is that the sun forms, the densest bit in the middle, nuclear fusion starts and the sun forms. And then the planets grow from the leftover bits, the dust, ice and gas that are kind of circulating around. And they stick together, these little bits, they start to stick together by electrostatic attraction, just like your hair sticking to a balloon you rubbed on your jumper. And then as things get bigger, you get collisions, you get smaller bits colliding with the big bits, and slowly they get bigger and bigger and bigger as the big ones kind of cannibalize the small ones. And so you get the planet accretion, more and more bits fall on it. And of course, as it gets bigger, you've got all that heat trapped from the radioactivity, and you get melting because of that radioactive aluminium-26. In the first couple of million years, that will generate enough heat to melt any planet more than about 20 kilometers across. And as that happens, you get the elements and the minerals separate out. So the dense molten iron and nickel and gold and iridium and platinum and things like that, that will sink down to the core because it's dense. And unfortunately, the cheap stuff, the aluminium and the silicon and things like that, will tend to float to the surface. So we lose all the valuable things at the core, and we end up with all the cheap stuff, cheap, less dense elements at the surface. And that's what Earth is like. We have an iron core and we have silicate outer bits. And so some meteorites are actually fragments from these little differentiated planets. So here we've got a core here. Iron meteorites are bits of cores. You've got the crust, and those crystalline meteorites, the achondrites, are bits of the crust of these little planets. And then there's a zone here called the mantle, which is made of olivine. So where you get these beautiful pallasites, the stony iron meteorites, they are somewhere near the core and the mantle, where you've got olivine mixed in with iron metal. So some of our meteorites come from fragments of these, what we call differentiated planets, planets that have separated out into their different constituents. But they're a minority. You're talking less than 10% of the meteorites are from these. Most of the meteorites are these chondrite meteorites, 85% of all meteorites, and they're made of these tiny little rock beads. This is a meteorite actually that fell in Northern Ireland in 1969. You can see them sliced through, and this is what they look like in 3D. And here's you've got one that obviously was still soft when it kind of bumped into another one. So it's made that little dent, you see. You think, but these are quite different. They don't match anything really on Earth, and they don't fit in with that model. So where have they come from? Well, think back to those planets that were forming in the first 1 or 2 billion years, lots of radioactive dust, and they melt. And remember, there's going to be thousands of these planets in the solar system, and there's no traffic control at all, so there's going to be lots of collisions. And that's what you would have got. You would have got collisions between molten planets. And if you've got a molten planet colliding with another molten planet, or even with a solid one, you're going to get huge splashes of molten rock and molten metal splashed out into space. And it's quite cold in space, so they will cool quite quickly, and they'll form little rock or metal spheres that are kind of floating around in space. So that's where the chondrules come from, colliding molten planets, which is an amazing to think. We had the early solar system was full of these molten planets crashing into each other. Who would have thought? But of course, the thing is that these things, if they then go back into another planet, the radioactivity will heat them up again. But if some of them survive out in space and then they kind of collect together again, say 4 or 5 million years later, there is not enough radioactivity left to remelt them. And that's how the chondrite meteorites form. The chondrules form a bit earlier than the chondrite meteorites that they make up. And when did it form? When did the solar system form? Now, this is a very easy number to remember. 4567, 4,567 million years ago. And we know that amazingly precise number, and it comes from measuring the radioactive decay of uranium to lead. And it's been done again and again and again on these things, these weird blobs that you find in certain types of meteorites that have been very barely altered since the beginning of the solar system. And these are called calcium aluminium enriched inclusions. There's a clue in the name that they contain calcium minerals and aluminium minerals. They're high temperature minerals. They were the first solid things to cool and solidify at the beginning of the solar system. The oldest dated material in the solar system, 4567. So you'll all remember that, I hope. 4567 million years is the age of the solar system. Now, here's a little graph, and you'll think, oh, it looks very, very complicated. I don't want to look at this. It's not really. This is actually lots and lots of dates of different types of meteorites that's all been put on one thing. And I've simplified it here. So these are what's called the CAIs, the calcium aluminium inclusions. This is the age of these, and they come out of 4, 5, 6, 7. There's a little bit of a spread, but the vast majority of them come out as actually 4, 5, 6, 7.3, not 0.72. This is an old thing. So that we take as being year 0. Everything happened from that point. That's when all this dust with the aluminium 26 in it started out. And so the clock is ticking, and you've only got 1.5, 2 million years really to sort of seriously melt things before you run out of energy with the radioactive dust. So that's year 0. Then we go on to the iron meteorites, and that's where planets have actually formed and they've melted because there's so much radioactivity from this aluminium 26. The planets melt and the iron separates out, and the cheap stuff, the aluminium, the silicon, goes to the surface. And these tend to be ages round about, up to about 2 million years after year 0. And then we go to the chondrules. Remember, the chondrules are forming. These are these planets that are molten, so they're busy melting, and the iron is sinking to the middle, but they're still crashing into things, and they're generating all these molten splashes that go out into space. And the ages of these, some of them are only kind of 500,000 years after, but they go on to about 3 million years after year 0. And then you don't see any more because there's not enough aluminium 26 left to really kind of melt these planets. So they run out of steam. But then you've got all those chondrules, and the late ones will just be floating around in space. And over time, they may then actually collect together, accrete together to form the chondrite planets. And they are forming after the time when there's no aluminium 26 left, so they can't remelt. And so the dates we get for the chondrite meteorites, the stuff in between the chondrules, is 5 to 10 million years after year 0. And so you can see there's a very definite sort of planets have already formed. They're forming within a few 100,000 years at the beginning of the solar system, and they're sorting themselves out, iron cores and such like. They're crashing into each other, creating these huge splashes of molten droplets of rock and metal, and then those bits are being kind of collected together to make these chondrite planets. And then we've got what's called the achondrites, and basically they're volcanism, volcanoes on the differentiated planets. So they will be starting very early on. You're talking within 1 million years of the start of the solar system, and they'll actually be going on for quite a bit longer, 10, 20 million years. And in fact, Mars is an achondrite, and Mars has been volcanic really quite recently, last 200 million years. So there's very definite sequence of events, and it's all tied in with the decay of this aluminium-26. And by 3 million years after the beginning of the solar system, there just wasn't enough left to do anything much with it. So to sort of summarize, we know how the different meteorite types formed. It's the aluminium-26 heating up these kind of planets of dust so that they melt, and some differentiate out into the planets with an iron core and silicate outer layers, and some are going to be colliding with each other, creating these splashes of molten rock and metal. And we know where they come from. They come from the asteroid belt. Today they come from the asteroid belt, but did they always come from there? Was the asteroid belt there in the early solar system or not? Because there's a really peculiar mixture of meteorites that come from the asteroid belt. Sort of things you think, no, they really shouldn't be in the same place. So what we do is we look at this horrendous list of different sorts of meteorites and try and work out, is there some other information in amongst all these different things that tells us something? And what we do, we look at their element isotopes. Every element has different sort of isotopes. So there's carbon-12, which is most carbon, carbon-13, which is a relatively scarce isotope of carbon, where it's got 6 protons and 7 neutrons, and then carbon-14, which is carbon-dating, which is radioactive. So lots and lots of element isotopes. Don't worry yourself about those. We've got all the iron meteorites, we've got the achondrites, the stony irons, and we've got chondrites, which fall into 2 groups, the C group, the carbonaceous ones, and the non-carbonaceous ones. And these are carbonaceous chondrites. Carbonaceous chondrites, surprisingly enough, are rich in carbon and water as well. It's clear that they have been altered or affected by water. Some of them contain up to 15% water mixed in with the sort of minerals. And it's clear that these formed from dust that contained a fair bit of ice. So that suggests that they perhaps formed quite a long way out in the solar system, where they weren't basically cooked by the sun. And they come from what we call C-type asteroids, which are these kind of dark carbonaceous type asteroids. And the marvelous Winchcombe Gloucestershire meteorite that just fell last week and was announced today is in fact one of these carbonaceous chondrites. And they're really quite rare on Earth because they're so crumbly. It's such a struggle to get through the atmosphere. And the other sort are the non-carbonaceous chondrites, very little carbon or water, and they clearly form from dry dust. And they come from what's called S-type asteroids, meaning silicate-type asteroids. And this is one that fell in 2013 in Russia, the Chelyabinsk meteorite. Some of you may remember the amazing fireball and thousands of people being injured by windows being blown out by it. So that's the Chelyabinsk one. And these are much, much more common. So you've got carbonaceous chondrites and non-carbonaceous chondrites that are quite different. And we think these formed somewhere in the inner solar system. We think these formed somewhere in the outer solar system because they had lots of ice mixed in. And what has been done this is relatively new stuff. This is in the last sort of decade or so, just over a decade. So people have been looking at element isotopes, and they've looked at all of the meteorites, and they look at different things, like titanium-51 against chromium-54, ruthenium-100 against molybdenum-94, and they've done them with a whole range of different isotopes. And don't worry yourself at all about all these things. The thing is, you can see quite clearly there's pink patches and there's blue patches, and that's the take-home message. And you can see the blue patches here. It's all those carbonaceous chondrites and things. The CM Winchcombe, the Winchcombe one is a CM chondrite. And then you've got down here, these are the non-carbonaceous ones. What's that? Ordinary chondrites and uralites and various other things like that. So they're quite distinct. And then you look at these other things, and the important thing here, these are the iron meteorites. So somebody's done the same thing with iron meteorites. You would have thought, but iron meteorites are quite different. You know, they're from the cores of planets. But you've got the you've got one group which we call the non-carbonaceous iron meteorites, and they plot out quite differently from this group here, which are much scarcer. They are much scarcer, but this group plot out with this lot, and this lot plot out with that. So you've got two very chemically distinct groups of meteorites, and you've got ions in there, and you've got ions in there, and you've got chondrites in here, and you've got chondrites in there, and you've even got pallasites in here as well. So essentially, you've got a carbonaceous group and a non-carbonaceous group. And when you look at the timing, I'm not going to go into the details of how this has been done, but we can actually work out when the iron cores formed. The non-carbonation iron cores formed quite early. You can see like from just a few 100,000 years up to less than 2 million years. They formed quite quickly. But the carbonaceous iron cores, they formed a bit later. It was a much more of a struggle for them to actually melt enough for the iron to sink down to the center of these planets. And the reason for that is because they must have been forming in the icy outer solar system. So mixed in with all that dust was a lot of ice. And so before you can start melting the metals, the iron and nickel and the stony elements, you've got to melt the ice first. And that takes an awful lot of energy. So it fits in with the carbonaceous things and the non-carbonaceous when they're quite separate, and they've been kept separate in the first few million years of the solar system. So how and when were they separated? Well, this is a really sort of simple schematic. This is the time after solar system formation. So this is year 0, and that's the distance from the sun. So the sun's in here, and that's getting further away. At the very beginning, first few 100,000 years, things are moving in towards the sun, and the non-carbonaceous iron cores form because it's dry dust, it's near the sun, it's had all the water sort of evaporated off, so they form really quite nicely, form very quickly. But then Jupiter forms. Jupiter clearly formed very quickly within the first million and a half years, and it got really big. This is about 20 times the size of Earth. And that gets in the way. So these iron planets that are starting to develop their iron cores, they want to move inwards because things want to move inwards in the solar system. They can't because Jupiter's in the way. So that it's blocked, and it keeps these two groups separate. And so these groups, and Jupiter's getting bigger and bigger. It's cannibalizing more and more stuff. And so you've got lots of these planets, kind of the chondrite planets forming, collisions between molten planets. You're getting them forming in the inner solar system, and you're getting them forming in the outer solar system. But they are kept separate. So for still 3 million years later, they are still just quite distinct. And then round about 4.5–5 million years, Jupiter starts migrating inwards. That's the whole story in itself. And asteroids scattered inwards and outward. Utter chaos. And what happens? The asteroid belt, it turns out, is actually a cosmic refugee camp. So this migration of Jupiter meant that these S-types, stuff made from dry dust, went outwards towards what is now the asteroid belt, and the C-types and the watery ones and Earth water went inwards towards the asteroid belt. So it's a mixture of stuff from all over the solar system. It's a complete hodgepodge. It's a kind of builder's rubble, as it were, that's been dumped. So hopefully you followed that. I'd like to kind of really conclude in, what did meteorites ever do for us? Well, who cares about them? Well, they help build our planet. They are fundamental to how our planet is. Our planet is part of the whole solar system story. And it formed quite early on, and then you have loads and loads of meteorites. The early days, we would have been bombarded all the time. It would have been magnificent. So they help build our planet. Meteorites are much cheaper than sending a mission to Mars, the Moon, or an asteroid. The Apollo missions cost $25 billion back then, $152 billion today. Curiosity rover and Perseverance just landed $2.5 billion. Hayabusa 2, which is sampling an asteroid, and it's just returned to Earth, actually. A cheap one, actually, at $150 million. But meteorites, they land on Earth for nothing. But of course, you've got to find them. They make some great tourist attractions. The really big meteorites. This was actually this is Meteor Crater, made by a meteorite, not a meteor. It's about 1 kilometer across, and it was made by an iron meteorite about 30 meters across. And fantastic tourist attraction. I mean, look how close it came to hitting the visitor center. Anyway, so there you've got some great tourist attractions made by the big meteorites. Precious metals, I said in the very early part of the history of the solar system, the planets melted and the dense elements, the iron, nickel, gold, platinum, iridium, and all those expensive elements and platinum that we like, they would have gone down to the core. And we would have had very, very little of that sort of stuff actually on the Earth's crust. All the gold and nickel and platinum that we mine has arrived later, after the Earth had differentiated and the crust had cooled and the inner core had become quite distinctly separated from the outer crust. So basically, the precious metals we mined come from a thin veneer of meteorites that kind of peppered the Earth relatively late on, hundreds of millions of years right up to the present day. So we owe all our precious metals to meteorites that arrived after the main party, as it were. Water. Our water comes from meteorites. This is, I was saying about isotopes. Hydrogen has two main isotopes. It has most hydrogen, nearly, all but 1 in 1,000 is the bog standard hydrogen. And there's a few bits of what's called deuterium where it has a neutron as well. And we can look at the water in various things, in various comets. I'm not going to go into how this is done. Moons of Saturn, the giant planets, interstellar medium. And it turns out that the closest match to Earth's water in terms of heavy water, which has a lot of this deuterium in it, and lighter water, which is mostly this, the closest match is those carbonaceous chondrite meteorites. And in the early history of the Earth, we would have been bombarded by vast numbers of these things. So probably a lot of Earth's water was delivered as part of the carbonaceous chondrite meteorite package, because they contain up to 15% water. And then even more amazing, amino acids, which are the raw ingredients for life itself. This is actually the meteorite that fell in Australia, 1969. I could substitute the Winchcombe meteorite that fell last week for that. It is one of these same meteorites. And one of the things that will come out from the analysis of the Winchcombe meteorite is it's full of amino acid. That's not to say that there is life out in space that is the origin of these amino acids. What it tells us is that amino acids can actually be formed in space. And these meteorites that were bringing the water to the early Earth would also have been bringing vast amounts of amino acids as well. So you would have, in the early oceans, it would have been like an amino acid soup. It would have been ideal for life to be born, really. So we owe our existence probably to meteorites like this. And then finally, I just finished, meteorites make excellent museum displays. This is just the meteorite display at the Ulster Museum. Beautiful stony iron palisite slice there. And I think I'll leave it there. I'm hoping you've followed a good part of that. Yes, it really is a sort of fascinating subject, which takes us right back to our roots, literally, where we came from. Thank you very much. Right. So I'm happy to answer any questions.
Okay, Mike, there's been a few questions. Probably the first one, though, I'll just get Nicola to confirm the arrangements for the viewing of the video at a later date, because there has been a few questions come through on that topic. Do you want to answer that?
Hi, yes, everyone. The recording will be available after the event. It'll be up on the website, which is www.science03. That's the O is a 0 for 2003 when we were launched, .org, and that'll be available over the next couple of days, hopefully tomorrow.
Actually, I could go through some of those. I've seen some of these. There's a very interesting one here saying you showed a picture of the meteorite in the grass. Surely it would have been hot enough to burn the grass. That's actually a really, really fascinating thing, is that people tend to think they're going to be really hot because the air around them as they come down is at 4,000 degrees centigrade. And what it does is that actually heats up the outside of the meteorite and it melts the outside. But the thing's been in space for millions and millions of years, and it's pretty cold in space, you know, minus 200 or something. It's only coming down through the atmosphere for 20, 30 seconds at most. It's going really, really fast. The outer surface is melting, but that melted surface is quickly being whisked away, and the heat is going with it. And then the next kind of bit melts and so on. And so the main part of the meteorite never actually gets hot at all. And there was a case last year in Cuba. There was a whole series of meteorites fell, you know, basically broke up in the atmosphere and scattered in one of these strewn fields. And so some people saw these things kind of land, you know, just a few yards away, you know, size of a potato or whatever. And several of them reported that they immediately went over to pick the thing up, and they had to drop it because it was uncomfortably cold, because it was like, you know, minus 150, minus 200. And there have been reports before, you know, earlier that frost formed on these things. So really, really fascinating thing, and not what you would think at all. So so that's that one.
I can just jump in, Mike.
Yeah.
Because I clicked the wrong button for one of the early questions, and it has disappeared from the list. So if I can ask one that is not obvious there, and it's in relation to the chondrites.
Yes.
So there's a question from Bill Keane. What is the matrix in which the chondrules sit?
The matrix is actually a mixture of more sort of silicate minerals, silicate dust and metal. Really, it's pretty similar to the chondrules, fairly similar sort of minerals, and they're the same sort of minerals you actually find on Earth. And it's almost like it's leftover dust that's not got mixed up with the sort of planets. Or it might be dust that's kind of been knocked off the surface of some of the other planets. So yes, essentially it's similar sort of stuff. And sometimes you find some of the chondrites where they clearly formed when the chondrules were still actually semi-molten and plastic. And so they're all sort of stuck together. Like, you know, if you imagine you've got a whole load of jelly babies in a bag and they all stick together, they're just like that. And there's almost no stuff in between them.
Okay, there's a couple of questions from LKM Martin. The first one is, how big is the biggest meteorite?
The biggest meteorite is a thing called, it's the Hoba meteorite in Namibia, and it's an iron meteorite. It weighs about 60 tons. It's still where it landed, because, well, it's quite large. So 60 tons. Then there's the one that the guy was sitting on in Argentina. That's part of the Campo del Hielo meteorite field, and that's 37 tons. There's another one part of that fall that's 31 tons. There's some found in Greenland that were 34 tons. So big. All the big ones are iron meteorites. The biggest stony meteorite that fell in China back in the 70s was about 2 tons, because they're much less tough. Iron meteorites, you know, you can fall out of the sky and dung, they survive.
Okay. So another question that they had was, how hot does the air have to be to melt a planet?
Well, I'm wondering, in terms of the planets, when they melt, they're melting in the early solar system. They're melting from the heat that's generated inside, because they've had all this radioactive dust mixed in with the other dust, and it's trapped there, and so it just melts. So it's, you know, getting in the middle, you're talking 5,000-6,000 degrees centigrade. But to melt metal iron, you're talking up to about 800-900 degrees centigrade. To melt the silicate minerals, 1,400-1,500 degrees centigrade, something like that. The temperatures, I was saying, when they're coming in, the meteorites are coming in through the atmosphere, the air around them actually gets heated up to about 4,000 degrees centigrade. It's basically squashing the air. It's not friction. It's often said it's friction. It's the air in front can't get out of the way quick enough, and it gets squashed. And if you squeeze the air, all the atoms are bashing against each other. It's like a bicycle pump. When you pump a bicycle tire up, the bicycle pump gets warm. It's a bit like that, but on a more spectacular scale. And so it gets up to temperatures 4,000 degrees.
Okay. Another question here from David Orr. It says, fantastic, fascinating talk. Thank you very much. What kind of meteorite was the Tunguska meteorite? Were they able to work out where it came from?
There's a good question. Well, no, the thing was, it's so long ago, that's 1908, you see. there've been lots and lots of thoughts about what it is. It's more than likely, because nothing was ever really sort of found, it's more than likely it was either a comet, which is essentially just a dirty snowball, a lot of ice and dust, or a carbonaceous chondrite, a big carbonaceous chondrite. It was a very, almost certainly a very crumbly meteorite. And they are actually, I said that they're really rare on Earth, and they're really rare because they're so crumbly and they just fall to bits. They struggle to get through our atmosphere. But actually in space, they are the most common types of meteorites. And we know that from on the moon. If you take a bit of moon soil and you analyze it, you find 1 or 2% of it is actually made of meteorite rather than actually moon rock. And overwhelmingly the dominant type of meteorite is these really flaky, crumbliest meteorites of all. So Tunguska was very likely, I suspect it was probably a comet, but it's difficult. There's nothing to show for it except a lot of flattened trees that have been there more than 100 years. So annoying.
Okay. I think we'll maybe get time for 2 more quick questions, do you think?
Yeah, yeah.
Okay. So first one is, why do meteorites break up coming down to Earth?
It's stress. It's basically, you've got incredible stresses as they're coming down through the atmosphere. They're coming down, they're doing, the Winchcombe one was doing 11, 12 kilometers a second, which is quite slow. The Chelyabinsk was doing about 19 kilometers a second, which is very fast. And as they come down, the atmosphere is getting thicker and thicker, and the stresses are just incredible, and they just basically get torn apart. So, and particularly this Winchcombe one, yeah, very crumbly. I'm surprised anything survives at all. Yeah, so it's the stresses. You know, you pedal fast on a bike, you can feel the kind of the pressure, yeah, the air against you. Imagine that at 30,000 miles an hour. Bit stressful.
Okay, there's one here quite popular for getting answered. Are there any records of anyone being hit by a meteorite?
Oh yes, yes. There was the famous. People should make a note of this and look it up. Annie Hodges in a place called Sila-Corga in Alabama in 1954. She was not feeling terribly well. She was reclining on her sofa, and this meteorite, which was kind of about the size of a football, crashed down through the roof of her house, and then crashed through the ceiling, which is fortunate because it slowed it down. Then it hit the radio. It was on one of those old valve radios, and it bounced off and it hit her on her side, you see. And there's this amazing photograph of the doctor inspecting this spectacular bruise on her side. So she's the only person that has really had an obvious injury from being hit by a meteorite. There are other people who claim they've been hit by tiny little ones. Somebody in Uganda back in the 80s was hit by a tiny thing. But yeah, Annie Hodges, 1954, Sila-Corga. And she wasn't killed by it, but she was inadvertently killed by the effects of it, because there was a big legal case because she didn't own the house, and the landlady said, "Oh, it's my meteorite because it was my house." And Annie Hodges said, "No, it's my meteorite. It hit me. God clearly intended it for me." And it went to court, and all the stress of that. She ended up getting divorced, and she ended up dying young. And her husband said that it was the meteorite that killed her, about 15 years after it hit her.
Okay, there are quite a few other questions. I don't know, do you want to draw a line?
Yes.
I would continue if Mike can give short answers. I'm sure we can.
I'll do that. Yes.
Okay, that's fine. So the next one, well, we've got a young gentleman, Christopher, who's 11 years old, and he's asking how, there's actually 3 parts to this question.
Actually, I can see it. I can see how do scientists think that Jupiter formed, what would happen to Jupiter if a meteor hit it when it was still being formed, and what would happen to a meteorite if it hit Jupiter now. The basic thing is Jupiter was so big, it was swallowing up anything that came anywhere near it. So Jupiter, if a meteorite hit it, a comet hit it a good few years ago, and it just made sort of, splashes, but it just, I don't care. That's how it got so big. It got to a certain size, and then its gravity is so huge, it just sucks in everything. And that's why you end up with a depleted zone where there was not enough material to make a planet where the asteroid belt is. And that's why Mars is small, because a lot of the material that might have made a decent sized planet where Mars is was stolen by Jupiter.
Okay. Next one from Sheena Lee. How do amino acids form in space?
I know, Sheena. Yes, well, that's a very good question, which I'm not entirely sure of. It's there's all sorts of things going on. Yeah, there's kind of cosmic ray, there's energy sort of out there. So quite how it is actually happening is a good question, and I shall get back to you on that, Sheena, because it's Sheena's a biologist. She likes amino acids, so I'm yeah, she put me on the spot.
Okay, and next one, who owns the Winchcombe meteorite now?
Well, there's a few pieces that have been found, and they've gone to Natural History Museum and Glasgow Imperial College. Edinburgh have got pieces of it, you see, and they have agreed with the landowners. The landowner ultimately owns it, but I think the landowners have been very generous, and they have said, yes, we agree that this is important for science, so we're kind of handing it over. So that's ultimately who it belongs to. It belongs to the landowner. They are free to do what they like with it. Though with this particular one, there is actually an embargo on exporting it. Nobody is allowed to export this one because it's so rare and unusual for the UK.
Okay. Where we find a meteorite crater, is the meteorite still there, or does it disintegrate?
It depends. A big crater like Arizona crater, basically, it's the energy of impact. It's still going very, very fast when it hits. It's doing 11, 12 kilometers a second. It disintegrates and vaporizes. Small ones like the Winchcombe meteorite, they get slowed down by air resistance. So they're doing a couple of 100 miles an hour when they hit the ground. So they don't make a crater, and you do find bits. The faster they're going when they hit the ground, which generally corresponds to how big they are, the less chance there is that they will survive because they just wipe themselves out. There's so much energy involved in these things that they just vaporized or shattered. So,
okay, from Karen Devoyle, why don't we get meteorites from Venus?
oh well, the problem with Venus is in order to fling bits off, you can do it on Mars, you can do it on the Moon. Big rock hits those places, flings bit off. Moon, no atmosphere, so no resistance. Mars, very little atmosphere, not much resistance. Venus has a hugely thick atmosphere, so any meteorite that to get through the atmosphere and hit Venus has got a hell of a struggle. And so it might actually knock bits off, but they're going to be smaller bits. And they've got to go through this atmosphere that's 200 times thicker than ours. So they burn up on the way out. So that's, and also it's nearer the sun. And the sun is like a very, very deep well. It sucks things in, its gravity. In theory, you might get something from Venus, but it's very, very unlikely because of the atmosphere mainly. Things burn up on the way out as well as on the way in.
Okay, there's one here from David Shand. Will meteor impact patterns
we're present on Mars' surface indicate if water was present on the surface of Mars during a collision in the past? Yeah. Yeah, I mean some of the craters actually on Mars, which are caused by big meteorites or small asteroids, and they're quite clearly what they've done is they have mobilized ice, water ice, beneath the surface, and you see these great lobes of what clearly was quite wet sediment going out of the craters. So it's very interesting because a big meteorite impact will generate a huge amount of heat, and that will have a huge effect on a planet like Mars, which is pretty cold, where most of the water is going to actually be locked up as ice. It releases a lot of this ice as water. So that's one of the issues about figuring out what's going on Mars, is that was this liquid water, liquid for a long time, or was it just been mobilized by an impact and the heat from that?
Okay, so the next one is from Tommy Bakey. Do meteorites make a sonic boom when they go by like a plane does?
Yes, they do. And the people heard the Winchcombe meteorite. If you want to hear a sonic boom in a meteorite, just look up on YouTube Chelyabinsk meteorite, and the sonic booms for that were just absolutely awesome. I mean, this big sonic boom smashed thousands of windows. So they do, because they're going at supersonic speed. And with Chelyabinsk, there were so many bits going at supersonic speed. It's boom, 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 boom. It was just awesome. Most awesome event I've ever seen in my life. That just amazing.
Okay, I'm noticing that as soon as we tick one off, we seem to get new ones. So I'm wondering where you want to draw a line.
Oh, I keep going.
Yeah, could we go to the last one or two, please, now, Gordon?
Yes, okay.
No problem. Right. So next one's from Douglas Fontaine. And he's asking, there is no such thing as a perfect vacuum, therefore is the starting point gas vapor?
I think it means in terms of the solar system forming. Yeah, there's always stuff out there, but it's pretty thinly dispersed. So the initial thing would have been this huge cloud of gas and dust, very, very dispersed, huge, several light years across, and then it's being compacted by the shock waves from the supernova actually kind of pushing it together, and then gravity starts taking over and pulls things in. So gas, dust, yes.
Okay, so I think this is probably an appropriate one to finish with, because I'm sure there'll be quite a few people out there will be wondering this. Are meteorites worth a lot of money?
They're much more valuable to science. Some of them are, you can pay ludicrous amounts of money for some meteorites, but frankly, they're not very attractive to look at. And like I say, the thing with the Winchcombe one is if anybody finds one, they're not going to be able to you need to know, how to sell the thing and who to sell it to, and you need to authenticate it, and you're not going to be able to sell it to most collectors are in the States, and you're not going to be able to export it and such like. So some of them can be lunar meteorites, can be hundreds of pounds a gram, much more valuable than gold.
Okay.
One more. Are you going to do one more? I saw one that was about cosmic rays. James Ferguson. What is the source of cosmic rays, and do they impact the bodies in the asteroid belt? And if so, how do we differentiate between the neon 21 generated belt? Cosmic rays come from supernovae, these exploding stars. And so they're sort of sending out these incredibly high energy particles that kind of zing through a meter of rock and then strike an atom and change it to neon 21. So they are kind of all around us in sort of space. So the neon 21, we know it must have been generated by cosmic rays. You get cosmic rays from the sun as well, but they haven't got the same sort of energy levels. They can penetrate a few centimeters, but the really sort of supernovae ones go straight through you, like knife through butter.
Thanks, Mike. I'm going to have to stop you there. We'll go on and on. So I'd like to thank everybody for attending this evening and offer our thanks to all Mike and Gordon for joining us. And thanks to everybody that submitted questions. I'm sorry if you didn't get them all answered, but I'm sure there'll be a chance later to ask questions. If you enjoyed tonight's presentation, there's still time to sign up for Hunting for an Impact Crater, in which Mike will tell us how he stumbled across the UK's biggest and only meteor impact crater beneath the town of Lairg. And tomorrow night, Wednesday, former astronaut Dwayne Digger Carey will join us all the way from Colorado to tell us about the latest plan to visit and eventually live on the moon, which sounds great. That's at 6:30, starting at 6:30. So please sign up. All event details are available on science03.org. Everything is free. Thanks again for joining us, and we hope that you enjoy the rest of the 2021 Caithness International Science Festival. Thank you.
Right. Thank you very much.
Bye.